Hi, welcome back, everybody. So we'll start the morning session. If you don't know who I am, I'm James Sparks. I'm a member of the Maths Physics group here, but I'm currently also head of the Mathematical Institute. We're really delighted and excited to be hosting this conference, bringing mathematics together with high energy theory and condensed matter physics. So thank you to the organizers and particularly Sakura for bringing this conference to us, to the Maths Institute. So it's a pleasure to be chairing the session today, and we'll get going with today's first speaker, which is Paul Fendley, and he's going to tell us about the uses of lattice topological defects.
Indeed, thanks to Sakura for organizing this, and of course for inviting me. I don't sit in this building, another lovely building, about an 8-minute walk away, so you can give tours of that if you'd like. Since it is a wide audience, which I think is great, I thought I'd give a kind of broad talk on the uses. So that wasn't just a tribute to Sidney Coleman in the title. I've gotten asked by friends of mine, both on the Hep string side and on the condensed matter side, what good are non-invertible symmetries? Even someone in this room said this to me. Won't out that person. So hopefully in the course of this talk, I'll be able to give you at least some answers to that question if you don't know any already. Anyway, it's work I did a few years back with Dave Asen and Roger Mung. And some more stuff with Louise Atkins here, and you should talk to her about some of this stuff. So just one slide of overview, just in case someone stumbled into the room not knowing what this conference is about, and maybe showing my angle. So the way I like to think about this problem that we're all working on in various guises is as being that of topological defects, and they implement all these symmetries. There's lots of names. There's at least 4 I gave, none of which I think are actually perfect, because there's lots of interesting examples that don't fit any. We pick any one of those, and I can give you an example that this doesn't fit. But the key thing is that we all make topological defects. They're independent of the location, and so then you can draw pictures like that one there, where it just says how they wrap around. And so you get these graphs that are labeled. So you're labeling the topological defect, and by some thing, and I'll explain what those things are, at least in the examples we study. And they can wrap around cycles of a torus and all that. But I emphasize what's so super interesting about this. These are symmetries, or at least sometimes they're symmetries. And but they're not the usual unitary symmetries if you look in a quantum mechanics book that people say what defines a symmetry. So what I'll talk about today, I'll go through some of these uses, and I'll give you a pretty quick overview. I realize not everybody knows what the lattice kind of things I do, so I'll try and keep that fairly brief, but please interrupt if you don't, and then I'll go through these uses. Oops, I did not want to go that far. So there's the uses, so I won't name them now because I'll get to them in a bit. Then the 2 uses I almost certainly won't get to involve adding braiding to the story, but happily Louisa has a nice poster on our very new work from just last week, and since she's the one who did most of it, she's much better equipped to tell you about it than me, so please go talk to her if you're interested in 2+1D and chiral topological order. So anyway, so the story, this is now the kind of overview part of the talk, but there's a really interesting story that has a lot of interesting antecedents. But it's that if you build lattice statistical mechanical models in a certain fashion, I'll outline how that works, then the topological defects come for free. And that's really amazing. You get stuff for nothing. I've gotten objections from my friends. It's like, how can this result be so trivial? And I mean, meaning, you just write down the model and basically the answer falls out. But the key is in the structure, and the structure is that of a fusion category, which I'll outline in a minute. But I just want to give a shout out to a lot of in fact, most of the basic work on this was done in the 80s, 70s and 80s. In particular, even not theory, but then the certain predecessors. And there was a beautiful observation by Fagan et al. One of the all is Jehan, who's here somewhere. And then we sat down and explained how to do this more generally. And the moral story I'm going to show you is draw pictures. And so what the fusion category brings to this story is a way to turn what I like to call a fusion diagram into a number. And what I mean by a fusion diagram is a labeled trivalent planar graph. And everything I say can be generalized greatly, but that's the cases I'm going to focus on here. And this comes up in a bunch of places. Again, I mentioned knot theory, Fagan et al., the station Q group, were thinking about then were anion chains. Came up a classic work of Moore and Seiberg in rational conformal field theory. But anyway, the upshot is you get some diagram. This one turns out to be an important set of manipulations. And you get manipulations that allow you to show that various diagrams with various physical meanings are equivalent to each other, but also at the end you can turn these things into a number. And that's exceptionally nice. So you get all this structure, and we, being physicists, can plunder this structure, and that's what's so remarkable about this stuff. So, okay, this is just one slide. I just want to give you a very quick overview of what this is. So basically, a fusion category is a set of objects, ABC, just a bunch of things, has to be finite, it doesn't really matter. And they satisfy these fusion rules. So everyone in here is familiar with this in one context or another, like taking tensor products of representations of Lie algebras, like operator product expansion in conformal field theory. And so you fuse these operators together and get a linear combination of other objects, and then these things are non-negative integers that describe the fusion, so 0, 1, et cetera. And then there's a couple other numbers, so the quantum dimension associated with each of these objects, that's a number. And then there's these F symbols that I'll give a quick overview. And so, like I said, you can use this fusion category. It tells you a unique way. I draw one of these labeled trivalent graphs. The labels now are objects in the category. And it gives you a unique way to turn that fusion diagram, planar one, into a number, which is pretty remarkable. And so the rules you prove that the rules are consistent and so forth. And so, for example, one of the rules is you have, this bit, you have a bubble, and you can get rid of it. And then to get this invariant, this number, there. So I should have said this number is an isotopy invariant. You can bend and twist the graph, and it's the same. The F move, again, I'm not going to belabor this because I'm not going to give many details in this talk. But then if you have this sort of arrangement, you can then change it to this. In field theory, again, this is ST. Mike Friedman, I remember, once said, well, this is the HI move. And I looked baffled why it's ST. But then if you look, that's an H and that's an I. So I don't know when Mandelstam named these in field theory. Should have called them S&T. But again, so this was the one slide, the quick overview of this. But the key thing is there's a bunch of rules. You get this list of objects, you get some fusion, and there's a bunch of rules to then turn this fusion diagram into a number. And that's, I hope all you need to know about fusion categories for this talk. So then the models I'm studying, so I'm going to do lattice models, and there's, I think, lots of good reasons why one should do it, which hopefully I'll illuminate throughout this talk. But so just to describe the models I'm defining, so what they are is the degrees of freedom live on the vertices, the sides of a lattice. Let's just stick with square lattice for this talk, but it doesn't really matter. And so I call these things H's. So they'll call them heights. And each point gets one of these things. And for those of you who know how this works, you can transfer matrices or quantum Hamiltonians with this. But here I'll just write down the partition function of this statistical mechanical model. So you sum over all the allowed height configurations, and we'll say a little bit more about how that goes in the models I'm interested in. And then you take the product. So by the square, I mean a number, the Boltzmann weight. It depends on the 4 heights around this face. In the old days, they called these interactions round a face models, IRF models in the 80s. when Baxter was first studying these things. And in the case we're studying, the heights are objects in this category. So we pick a category to begin with, and then the allowed heights are objects in this category. We can make additional restrictions. And then it immediately follows, once you specify one more piece of information, I'll tell you about in a second, what the allowed Boltzmann weights are for if you want all the nice things I'm going to describe what happen. So the category not only tells you what the degrees of freedom are, but it tells you how to write down a Hamiltonian or transfer matrix that has nice properties. And so, for example, the Ising model, I'll explain how, can be written in this language. And so what you get there, what turns out to be extremely convenient, is to do something that looks funny initially, which is to just take the Ising degrees of freedom, so usually plus or minus 1, but for reasons that will become apparent, I'll call those 0 and 1, the 2 degrees of freedom. And in the Ising model, you just measure whether these things are the same or different, and with some weight, and then you do this sum over all configurations, and then take the product of this factor over all of the faces of this lattice. So that's the kind of model. I'll do more. The whole point is to do lots more complicated models. The Ising, but just to, so again, if this is too telegraphic, please ask. So now let me give you a few examples, or a set of examples that I'm going to confine myself to in this talk. So in the old world, we called this SU2 level K, SU2 level K, and so these fusion rules, remember I say you have a bunch of objects. So here we truncate the representations of the Lie algebra of SU2, and using physicist notation, I guess most people are physicists, we label them instead of 0, 1, they're 0, 1 half, 1, where 0 is the identity representation. But we truncate them. And the fusion rules then have to truncate. So you can't go to arbitrarily high spin. But for example, in the simplest non-trivial case, which is SU2 level 2, where this index K is 2, well, then we have the usual take 2 spin-a-half representations of SU2, or 2 spin-a-half particles. You fuse them together, you get the identity plus spin 1. But what happens here now is if you fuse with the half, you're restricted. When K equals 2, you can only go up to 1, and you only get a half. And these pictures, I'll use a little bit in this talk. And so this is just a pictorial version of these two relations here. So I have a vertex on this picture for each object, so 0, 1 half, 1, those are the 3 I'm allowed. And then when I do fusion, so this picture represents graphically fusion with a half. So because 0 times a half is a half times a half is 0 plus 1, so I put edges there. So I put an edge every time there's a fusion. And again, I'm only going to deal with categories where there's no arrows or anything like that, but everything can be generalized. And then the catch is the one additional ingredient I mentioned on the last slide. The rule that we impose is that you pick now, so you choose a category to define your model. Now you choose one object in the category. So in this case, let's choose spin a half, and the nearest neighbors have to have a non-vanishing MEBC, so have a non-vanishing fusion with that special object. So in this case, 1 half. So that's that was a lot of words, but maybe this picture is helpful. It just says if you have a 1 half, it can be next to a 0 or a 1, but a 1 always has to be next to a half. So for this picture I drew in the last thing for a square lattice, you'll see, of course, you get 1 halves on every other site. And that's why in Ising you get, that's why I get 1 on every other site. And so then I can do other examples. So a famous one, which goes under a bunch of names, is if I just now do, the next case, which is 1 tensor 1 gives me 0 plus 1. So again, I truncate. There's no spin 2. And so the picture looks like that. There's no spin 2. And then I can go up one more, SU2 level 4, which also has another name called rep S3. We should have put that in the paper, but anyway, so then it's this picture. So those are the models, and then the nearest neighbors in the lattice model. Okay, so that I think that's pretty much it for the defining the models. Now, I said the payoff, you're doing this and you can define topological defects very nicely. So I say this is basically automatic. Once you define the model this way, you choose the Hamiltonian appropriately, you get the topological defects for free. And so there's a procedure which I'm skipping, but basically what happens, we now just define the partition function including this defect, which I draw there, and then these have some weights too, like the weights in the lattice model, the bulk of the lattice model. And then along the defect, we have a special weight. And if we choose that weight specially, what happens is then they're topological. And so what happens, they basically have to commute with the ordinary bulk Boltzmann weights. But the key thing is the category just hands you solutions to this. You don't, I mean, so we proved in general in the paper with Dave and Roger that anytime you do this, you get a solution, you get topological defects, one for each object in the category. And so now that we know this, we can just derive identities. So this is looking seemingly obvious, but profound identity. Well, so it turns out in the category, if you just have a single loop, it's a special case of that bubble removal I wrote down a few slides ago. You just replace this loop with a number, the quantum dimension of that particular object, phi. And so it turns out, again, you can prove that this happens if I make a defect like this. Well, I get the same partition function as if I get rid of the defect and then multiply this factor. And so we then have this amazing identity between partition functions. So again, this is extremely non-trivial identity. It says that the partition function in the presence of the defect, so I drew that picture there. And by the way, the theory on one side of the defect doesn't have to be the same as the other. So it relates these two partition functions. So this is the same equation here. This is the partition function in the presence of the defect there, and they're the same. And I'll get to boundaries in a bit. Yeah.
So usually F symbol is complex. Even in that case, do you get a statistical model for complex F matrix?
I don't see why not. We never studied those in detail, but as far as we can tell, well, we proved this for any category, basically any fusion category we proved. So, and we didn't assume unitarity, we didn't do anything. So we never looked at those models. So what happens sometimes, however, is all this added data in the, making phases and all, it doesn't matter in the end. You can unitarily transform away. So there's no guarantee, even if you start with something funny, it may, in the lattice model, not turn out to matter. So we haven't checked that, but it'll work. The question is what model will get there.
Do you label the defects and all, or you don't label them?
Yeah, so there's one defect, right, so, so quick. Right, so there's one defect for every object in that. Actually, every object in the free-fall center. Part of the things, many things I suppressed here. And so, yeah, let me just blast through this because I want to get to the non-trivial one. So just sometimes people complain that I don't give enough detail. So here's a slide. These are the defects for icing. One curious thing I wanted to just note is, so the theory on one side of the defect need not be the same as the other. So it's a duality, if you wish. Oops. Sorry about that. So the theory shifts from one lattice, the original lattice, we had these empty sites, to the other on the side of the duality defect. But that's a feature, not a bug, because that's the way duality works. Kramer's 1A duality works. Okay, so, all right, so good. I've got about 10 minutes left, so I'll give you now the use, as many uses as I can get through. So Kramer's 1A is this fantastic old result. It really, to me, is the canonical example of a non-invertible, quote, symmetry. It's not really a symmetry. But this now generalizes, this categorical construction generalizes this to basically a slew of models. And again, you get to these, to what the category then hands you. It tells you that for every object, you have a defect, but then the corresponding defects satisfy the same fusion rules as do the objects in the category. So pictorially, you get this thing. So if I had an icing, if you have two of these duality defects I flashed on the previous slide, you put them together, well, you get something non-trivial. This is why it's not invertible, because you get the sum of nothing plus what's a spin flip defect. So That just comes out automatically and explains that. A tangential comment, but I think it's important. Kramers-Wanier duality in its usual formulation is not a symmetry because it, well, first of all, maps coupling to the dual coupling. When you change the lattices, you change the coupling. Now, you can specify the self-dual coupling, but even there, once you put boundary conditions in, it changes the boundary conditions. So still mapping between models. There's one limit, which Natty and Zhang Chao studied. If you take the Hamiltonian limit, if you take periodic boundary conditions, if you take the critical point, then you can turn Kramers-Wanier duality into a symmetry. That's the only case where that works. So another example, another famous model, the one that I'll get to in a few minutes in more detail, the Fibonacci model or the golden chain. Sorry, lots of names of that. So this one, it just has one kind of defect, and so when you fuse it with yourself, you either get nothing plus itself again. This is a canonical example of a non-invertible symmetry, I guess beyond Kramers-Wanier. However, it's invertible, so that's why I don't like the word non-invertible symmetry. In other words, this operator d tau has an inverse. So it is what it is, but that's why I like topological defects. All right, so then let me just summarize this use number one by just saying, I've said there's lots and lots of models, but to be more precise, I believe that there's at least one, and typically more than one model for every rational conformal field theory, meaning there is a lattice model that realizes in the continuum limit any rational conformal field theory, and this construction works. So it gives you exact lattice defects, I would believe, for every rational conformal field theory. It doesn't necessarily give you all the CFT defects, but more interestingly, if you take different lattice models with the same conformal field theory, you get different defects that turn in the continuum thing. But it's important to remember, this is nothing to do, in a way, with conformal field theory. Generically, you get lots of funny things. The category you're getting is not the category, it's usually a subcategory of the category of the conformal field theory. But you get complicated phase diagrams. I just threw that on there to show that impose this symmetry, you still get lots and lots of interesting physics. It's very rigid. Okay, so let me now give you a couple more uses. In the last 5 minutes, I'll try and give you some nice uses of it. So one is that you can use this to derive exact degeneracies in the spectrum. And there was an old result for certain integrable models, certain perturbed conformal field theory, that postulated this funny situation where you've got a double well. So the effective field theory for this particular integrable field theory is a double well, but it's not a symmetric double well. There's no symmetry, but nonetheless, it's exactly degenerate. And this was understood using integrability stuff and assumed to be kind of a very special thing, quantum groups and integrability and that stuff. But what we showed is that, in fact, there's a much easier way to see it. If you look at a lattice model, which realizes this model, this degenerate just follows from non-invertible symmetry. And again, it almost happens for free once you set this up. So yeah, let me go through this quickly because I do want to get to the other ones. So there's a Hamiltonian. This has a lot of names, but the key thing is here is that the Hamiltonian, that's just the explicit expression of each bit of the Hamiltonian. It's a sum of a bunch of local terms. They act on 3 successive spins in this model. But the point is the non-invertible symmetry commutes with each generator of the Hamiltonian individually. That's super, super important. So then you can take some extreme limit. So you take some limit, set half the couplings to be 0, the completely staggered limit. You can now trivially solve the model. All the terms in the Hamiltonian commute with each other. And you trivially solve the model, but then you see there's 2 ground states, but they're not symmetry related by any normal symmetry. But the non-invertible symmetry mixes them. And thus they have to be degenerate. But why that's spectacularly useful is because now we go away from this limit. Okay, we can't exactly solve the model, but we've got a symmetry. The symmetry, as long as the symmetry still holds, the non-invertible one, well, this structure has to persist, right? You can't just get rid of this without going through a phase transition. So you know the whole phase has to have this degeneracy, even though you can't solve the model exactly. I say this lattice model isn't even integrable. But even more, you can even get the excited state. So it's funny, in this double well, the basic excitations might expect, well, there's a kink between the two ground states, but then there's also what gets called in the Stein-Gordon language a breather, but a bound state sort of just within the shallower of the wells. There'll be one here, but it'll be higher in energy. But it turns out in this particular model, they're exactly degenerate. And again, the non-invertible symmetry gives you that. All right, so let me give you two more uses. One is, okay, so now we can do a more complicated model, has to do with Rydberg blockade experiments. Hello, at least one person on this. But then there's this whole nice web of dualities that Louisa Eck and I found. And so you can map a model, the XXE chain, a really well understood model. You can map it to this other interesting model, which, sorry, I don't have time to describe in detail, but you can ask me the questions more if you want. So these non-invertible mappings basically tell you now instantly that you look at this. This is a well-known XXE phase diagram. Sorry if you don't know what XXE is, but it's a well-known phase diagram. And then this non-well-known phase diagram, again, follows basically instantly. And you can interpret it. And again, you get this example, what in the XXE language is just the anti-ferromagnetic order, then becomes here this unusual ground state degeneracies, again, just like another example of what I gave. And again, the non-invertible symmetry explains why, the non-invertible mappings, sorry, from XXE. There are non-invertible symmetries, and then you can check that there's one that preserves that ground state. And then the curious thing, just as a moral, so I showed you on the previous slide this web of mappings between different models. I didn't define any of the models, but trust me, they're there. But the interesting thing, there's a model with a S3 symmetry, this three-state antiferromagnet in that picture I drew. And the very sophisticated non-invertible symmetries, it's even hard to write down explicitly. You can, but it's kind of nasty. But the way you can get it is you transform to the three-state model. It's just then a Z3 transformation of that model, the very trivial Z3 transformation, then you transform back. So it's saying that sometimes things that look awfully complicated are not. Another cute thing that, another cute is that there's a non-invertible symmetry that's a remnant of the U1 of XXE. XXE has a U1, but the other models don't. Right, so, okay, the last use, and then I'll stop. Yeah, okay, I'll do 1 minute of this. So I mentioned this, I drew this picture before of relating partition functions. So say on a disk, and so I have a partition function with no defect, but it's related to that of the defect times 1 over d. I wrote the d on the other side this time. But now what happens is a topological defect. So now I can then just push this defect out to the edge, then glue it to the edge, and then, so it's an operator on the edge, so it changes the boundary state. But because the defect and everything is super explicit, we know what this is. So we have an exact equality between this boundary condition and the boundary condition when you're acting with this defect. Everything I'm telling you is schematic pictures, but everything I just wrote out is utterly and completely explicit. And so we get this exact identity between partition functions. So this to me is just, so this is what I was thinking when I said at the beginning, get stuff for free. This is instant. So you define this partition function in this in this boundary condition, and then I define that partition function, and it's a precise relation. I've changed the boundary condition by acting with this operator, but it's there, And this number is just the quantum dimension of the corresponding object in the theory that we used to build the model and the defect. And so you exactly get this result there. So good. So this factor is called the Saflik-Ludwig G factor. We heard about that yesterday. So it gives a general result that says that the quantum dimension, it gives you the ratio of the G factors. And I think to anticipate Sakura's question yesterday, I think the issue Bear was complaining about is not the ratio, it's it's like, ask me again, I know more about that story if you. Okay. All right, good. Oh, yeah, let me just say one more thing. And you can compute conformal dimensions by doing modular transformation. So all that you can do explicitly and easily on the lattice. Good, so yeah, this was the one said I wouldn't get to. And since I'm out of time, I'll just put the conclusions. I'll say the moral. I know most people here are field theorists, and to some extent I am too. I think it's, if an interesting concept originates on the lattice, and Kramer's 1A duality, which I really think is the mother of all of this, is a lattice thing, it probably behooves you to keep looking at the lattice. Anyway, thanks very much.
Thank you, Paul, for that very nice talk. So we have, there are a couple of questions during the talk. We have time for one or two. Peter, thank you.
Thanks for a nice talk, Paul. Do you have any idea of how this nice story generalized to higher dimension? For example,
yeah, well, that's talk to Louise. Yeah, so we did 2 + 1D models. You have to add grading. Well, so in a more wrote a beautiful paper, and then Louisa and I, mostly Louisa, really figured out how to generalize that. Yeah, so these gauge fluxes in Kitaev then become one form symmetries become gauge fluxes in Kitaev. So it looks like the whole beautiful picture repeats itself, but the work there is just beginning.
So the follow-up question to that is that in that construction, if you're able to construct a topological order from the lattice construction, can you also engineer the sandwich picture directly on the lattice?
Yeah. Okay. No, so in fact, in fact, in our paper, you can even see this sort of sandwich picture and how we explain. There's multiple ways to explain why this works, and that's one of them.
Sakura?
Not have a question.
Yeah.
Or give it a thing, or just I'll repeat the question.
When you're talking about Fibonacci, you said that it has an inverse. Could you comment a bit?
Yeah, so d tau, just think the golden mean, right? Tau times tau minus 1 is 1. There were phi, the golden mean, right? So d tau times d tau minus 1 is 1.
But does d tau minus 1 correspond to a symmetry defect of some,
Well, all these defects are non-local, so yeah, I agree. It's sort of not a kind of thing, taking the defect and subtracting the identity defect. But it's a linear map on some vector space, so of course I can take linear combinations of linear maps, and that's the inverse. So it's to some extent a wisecrack, but it's worth not getting too worried about whether the thing is not. I think the moral is don't worry about whether it's non-invertible or not. It's interesting, and just go with it.
So maybe the distinction you want to make is between the lattice and the continuum. Maybe just a slight comment on that question. Maybe you want to make a distinction of discussing this kind of symmetry, version of symmetry on the lattice and in the continuum. On the lattice, indeed, there's no clear criterion on why you cannot take subtraction, for example.
Yeah.
But in the continuum, there's a criterion that forbids you from, taking differences between defects that's coming from requiring locality.
I'm curious. Maybe better. I'm curious why that is, but let's discuss that.
Yeah. Oh, okay. Well, let's wrap up here. We have a coffee break now. Can we thank Paul again?
Thank you.
So there's coffee outside. We start again promptly at 11:15. Thank you.
If you haven't received your name tag yet and you haven't registered because you arrived late, just come to the front, please.